Yesterday we derived the topology of the clock and data recovery without forwarded clock. The idea is you use a voltage controlled oscillator to generate the clock. Okay? And you detect the phase difference between the generated clock and the data using the same type of phase detectors we have used before. You can either use the binary or the linear phase detector. I will show the analysis with the linear phase detector because that's easier. Now, it turns out that if the VCO were at the right frequency, then you can pass the average, you can pass the charge pump current through a resistor and it provides the right kind of behavior to recover the phase of the clock. Now, the frequency is also off, so essentially you have to first bring it to the right frequency. To do that, you have to have a capacitor here. What happens is if the frequency is different, eventually this will get charged to the right voltage so that the voltage across the capacitor when applied to the VCO brings it to the right frequency. The voltage across the resistor provides these phase corrections for instantaneous phase changes. Okay, the data could be jittering around and so on. So that happens because of the resistance. And as we, even during the derivation, we decided that, we concluded that the C has to be very large. Essentially, you have to reach steady state with the resistor voltage being applied to the VCO and then use the phase shift between data and clock to update the capacitor voltage. Okay? Is this fine? So now, of course, we have to do the analysis quantitatively and see how things work out. To do that, let's assume that at the operating point, we have some phase theta d and this is theta ck, and at the operating point, obviously, we'll assume that the rising edges of the clock are at the center of the data. Okay, so it is locked correctly. Now, that is by definition our zero phase. All the increments are evaluated above that operating point. Okay, and there will be some control voltage here which will bring the VCO to the right frequency. Now, if you apply a phase increment to data, it will in general result in some increment in the control voltage and some increment in the clock phase. In fact, you hope that the increment in the clock phase will be exactly same as the data so that the clock head stays in the middle of the data period. Of course, that may or may not happen. So, and by the way, also for the charge pump at the operating point, the average output will be 0 and with this phase perturbation on data, you will have some increment in the charge pump current. Okay, is this fine? So we need a model that relates all of these things. What is the model for the phase detector? So the phase detector looks at the difference between phi d and phi ck, and its average output is ICP by 2 pi times the phase difference. Okay. So the output of this is the average current of the phase detector, and the incremental model of R and C remains the same. Okay, and here you get the incremental control voltage. Now, if you want to represent this as a transfer function, you would put ICP of S as an input, and the impedance will multiply the impedance of the series branch will multiply ICP, and you get V control of S in the S domain as the output. Okay. Now, what is missing is the VCO. So, what is the incremental model of the VCO? So, essentially, when you have this increment, the VCO will be operating at some frequency, right? So, at the operating point, theta clock, which is the theta VCO, right? This is equal to basically 2 pi f naught t plus 2 pi k VCO integral V control dt. This is the operating point V control. Okay. And with the perturbation applied, this would be, you will have the same terms plus okay. So this is the output phase increment when you have a control voltage increment of V control. Okay, is this fine? And if I express that in the S domain, it becomes 2 pi kVCO by S. Okay, so this is the model of the incremental model of the VCO. You would have seen this, but this is the reason for it. And then you get phi ck. I can also call that phi out. So that is the output phase. Okay. So now we started off by saying we will look at the response to a phase increment in the input data phi d, but the same model serves for any other increment that may happen. Okay. What are the other possibilities? First of all, you have the charge pump noise. Okay. And you can have the resistor noise, which could be represented either by a voltage source in series or a current source in parallel. In this case, a series voltage source may be more convenient. So you'll have the noise voltage of the resistor. And then we have not looked at the model of this, but the VCO again will not give you a perfectly periodic output, even if the input is constant. It will have its own noise. So its phase noise has to be added. Okay. So you have to add the phase noise of the VCO. Okay. And then this INCP could represent the random noise of the charge pump as well as any current pulsing that may be there because of the action of the phase detector. We know that in general, no phase detector will give you a constant output for a constant phase difference, right? It will have some average value corresponding to the phase difference, and it will always have some periodic disturbances. Okay, so that also could be modeled by that INCP. Okay, so the same model, the same incremental model is used to find the total output phase or any other quantity in response to either jitter in the input data or any of the other disturbances. Okay, any questions here? Okay, so now please find all the transfer functions, that is and finally you will have okay. The principles are exactly the same, only that now what is the order of the system? Second order. There is S here in the VCO. VCO is an integrator, and then you have this capacitor. So you get a second order transfer function. Okay. First evaluate this, and then you will have to sketch the transfer functions. During that time, you can assume that C is large, whatever that means. Okay. Or maybe before doing all of this, okay, let's do one thing. So this is a negative feedback loop. First evaluate the loop gain. After that, we can do all of this. First evaluate the loop gain of this negative feedback loop. That will right away tell us constraints on some parameters. And after that, we can evaluate all the parameters. Oh, by the way, the phase detector gain should have another factor, which is the transmission. So what is the loop gain? It's basically the gain around the loop. It's the product of all these things. So it's density factors times ICP by 2 pi. That's the phase detector gain. And then the impedance of the loop filter is R plus 1 by C. And the transfer function of the VCO is 2 pi kVCO by S. Okay. It's easiest to, if you do this, let's see, what is a good way? So this goes away. So density factor, ICP, kVCO by 1 plus SCR by S square C. So let me do it slightly differently. I will put an R here and then SCR and S. Okay. So what does the Bode plot look like? There is a reason I decomposed it like this. What is the Bode plot of the first part? It's just an integrator, minus 20 dB per decade. And then, what is that? Where does it cross unity? This number, okay? And then, what is that? What does the Bode plot of this part look like? It will start with a minus 20 dB per decade slope and then become equal to 1, okay? So, it could be like that, or depending on, it depends on RC, right? What is this corner? That corner is 1 by RC. So where do you want it? Like the red curve or the blue one? Or it doesn't matter? I mean, it could be anything, right? I mean, I could have 1 by RC over there. I could have 1 by RC over here. So which one would be preferable? Is there any blue one? Why? First, yeah, I mean, we already concluded that C must be large without specifying how much it is. So that means that it has to be to the left. Okay. So let's take the blue one. So this is the other factor. So what is now the Bode magnitude plot of the complete loop gain? So it will start with minus 40 dB per decade slope, and then changes to minus 20 dB per decade slope. Okay. Similarly, I mean not similarly. On the other hand, the phase. This is the magnitude of L. If you plot the angle of L, what does that look like? What does it start with? What is the phase at very low frequencies? 180 degrees. Okay. What is the phase at very high frequencies? 90 degrees. Okay. And the break point is here at 1 by RC. So there it will be how much? Okay. It will look like that. So now actually this tells you how large or how small C can be, right? Okay. So what happens if you move this, let's say you make the value of C smaller so that it moves to the right, it moves like that. What happens then? The loop gain would be, let me delete this part. So if instead of this I had it like that, that is I bring in 1 by RC very close to omega u, what happens? The loop gain would look like that, right? And then the loop gain phase would look like that. Okay. So now, what is the phase margin? All of you have gone through some course which teaches you basics of negative feedback, right? So you know what phase margin is. So when this crosses, when the gain crosses unity, you look at how far phase is away from minus pi. Because if the gain is unity and phase is minus pi, then it is unstable, right? You can have, you will have poles on the j omega axis and it will be an oscillator. So a measure of stability margin is to see how far it is away from that. Okay, that is you look at where the gain is 1, gain magnitude is 1, but the phase is how much the phase is away from minus 180 degrees. So that goes on reducing, and then if you make C very small, then your loop gain will be like that. Okay, so and your phase will look like that, and your phase margin will be really poor. Okay. So as usual, when I say C is large, I mean it's okay for sort of casual conversation. Finally, you have to say it has to be larger than what? Okay. That is true of any dimension quantity, right? So in this case, essentially C has to be large enough so that you have adequate phase margin in the loop. Okay. The intuitive condition that we had got, that it should settle before this starts acting on it, that is translated to this one. Okay. So the zero frequency omega z is 1 by RC and it must be sufficiently below omega u. How much below it is, that depends on other things. Okay. So it will be stable, but it may have peaking and other things that we will look at. Is this okay? What is the significance of this omega u? Unity loop gain frequency. What does it signify? Yeah, all the good things about negative feedback come because of high loop gain, right? Now, if you had to kind of demarcate crudely saying, here I have high loop gain, here I have low loop gain, the boundary between them is omega u. So, below omega u, you get benefits of negative feedback. Okay, of course, the change is gradual, right? It's not as though you go to 90% of omega u and then you have a lot of loop gain. You don't. But if you want to draw things crudely, below omega u, you get benefits of negative feedback, and above omega u, you basically it will be like an open loop system, roughly. Okay, that's the idea. So omega u is, so this omega u, the unity loop gain frequency, appears as the closed loop bandwidth. So if you calculate these things, right? So in general, when you evaluate things involving, I mean quantities involving, I mean transfer functions in a negative feedback loop, you will have terms of this form. L by 1 plus L, okay, where L is the loop gain, or this can also be written as 1 by 1 plus 1 by L. So what is this quantity when loop gain magnitude is very large? 1. And when the loop gain magnitude is very small? Huh? I mean, something better than 0, something L. Okay, so it is L. So the thing is, when the loop gain is very large, the expression doesn't depend on the loop gain itself, it becomes 1. Okay, so if I plot, for instance, if I have, I'll draw the same type of loop gain. So let's say I had a loop gain like this. This is L. What will be L by 1 plus L? What will that look like? So it will be like this, and after that it will follow L. Okay. So this unity loop gain frequency will be the bandwidth of the closed loop system. Okay. So essentially, the good stuff that you get from negative feedback is limited to this bandwidth, right? So if you want to increase the frequencies over which negative feedback is effective and your circuit behaves in a desired way, you have to increase omega u. Now here you see that omega u, of course, it is proportional to ICPR and KVCO, okay, and it's also proportional to the transition density. This again, I think we have got this result in many different ways. That if the transition density is small, right, you don't have enough information to correct for the phase. That's basically what happens. We saw this with the clock and data recovery with the forwarded clock also. There I didn't ask you to plot loop gain, but you can do that. You can do that and see. It will be, what do you expect for the loop gain in that case? What kind of curve do you expect? Huh? It will just be an integrator. Okay, it won't have this other minus 40 dB per decade part. Okay, and you can see that there also the unity loop gain frequency will be the bandwidth. But there we evaluated the bandwidth directly and found that it's proportional to the transition density, right? So here also we see the same thing. Is this okay? Fine. So now with this, it should be easier to plot the transfer functions. So please do that. Because I mean, you already know what the loop gain is. So you can write the expressions for the transfer functions and also plot the, you can plot the magnitude plots, that's enough. Plot the transfer functions, okay. So this is the loop gain L of S, right? And I mean, it's painful to carry all these terms, but they always appear together as a product. There is no need to do that. So this is omega u by S. You can write it in different ways. It's basically omega z by S plus 1, right? Okay. So phi ck by phi d, what will that be? The loop gain, it's all in the forward path, right? The feedback path is 1 here, isn't it? So what will this transfer function be in terms of loop gain? L by 1 plus L, okay? So it will be L by 1 plus L, and L itself is omega u S 1 plus omega z by S divided by 1 plus omega u by S 1 plus omega z by S, okay? Now it's always beneficial while plotting and for in circuits purposes to have it and sorted in powers of S and then have the DC term to be 1 if possible, right? So if you do that, basically multiply this whole thing by 1 plus S by omega Z, or rather omega, so you multiply both numerator and denominator by S by omega U, S by omega Z. What you get is, what do you have in the denominator? What will be the S term? S by omega Z plus 1. And in the numerator, okay. 1 plus S by omega Z. So this is quite easy to calculate. The interpretation is more important. And now I also said this is easy. What is this now? Phi and VCO is added here. That is the output. And you have the rest of the loop. So what will be phi CK by phi and VCO? 1 by 1 plus L. It's the, I think you remember this, right? If you have G as the forward path, H as the feedback path in a negative feedback setting, this is minus. From here to there, it is G by 1 plus GH, and from here to there, it will be GH by 1 plus GH. And if you add something here, from there to there, it will be 1 by 1 plus GH and so on. Okay? Or G is the forward path, it's the forward path gain divided by 1 plus loop gain. Okay? So, what will this be? 1 by 1 plus omega u by S, 1 plus omega Z by S. Again, I will multiply by S by omega u times S by omega Z. Okay? So, I will get this as the result. S square by omega u omega Z. S. The denominator remains the same. That's again a common feature, right? You will see that denominator of all transfer functions in a system remain the same. The numerators will be different. Okay. What about phi ck by I and Cp? Because this can be transformed to this side. It's the same as adding I and Cp divided by the phase vector gain, which is transition density times ICP by 2 pi. Okay. So it's the same as phi ck by phi d multiplied by this factor. Huh? Yeah. That is V and R, right? So this is that times and what about this one? Yeah. So first of all, adding V and R here is the same as you take ICP times this impedance and you add V and R to that. It's like adding it there. Okay? Which is also the same as adding it here with what? So it's basically like adding 2 pi kVCO times V and R by S. Yeah, correct. By S. Okay? So it will be phi ck by phi n VCO times this factor. And that was and this has to be multiplied by 2 pi kVCO by S. So this goes away. You will have S over there. And I'll also remove this omega u from here. I'll have S by omega Z so that it's the same as in the denominator. And then have omega u over there. Is this okay? And omega u itself was density factor ICP by 2 pi and ICPR by 2 pi times 2 pi kVCO, right? Okay. So if I use that, this becomes, this factor is also, it is okay. So this alternatively can be written as 1 by the transition density times ICPR by 2 pi. Is this okay? So what kind of transfer function do we have? Phi c k by phi d. What type of transfer function is that? Is it high pass, low pass, band pass? What is it? It is low pass, basically. It is one at very low frequencies. At very high frequencies, it goes on at 20 dB per decade. And it is similar to what we had without forwarded clock. And this makes sense. It essentially means that if the data is jittering around slowly, your loop will follow it. And if data is jittering around very rapidly, your loop cannot follow it. Okay? And similarly, this phi c k by phi and VCO. What kind of transfer function is this? High pass. At very high frequencies, it is 1. Okay, and low frequencies, it is very small. It's 0 actually at very low frequencies. Okay, why does that make sense? You look at the block diagram of the model, and why does this make sense? Hmm? So this is like negative feedback correction, right? Like noise cancellation. You add a noise here, and then you sense that, and then feed it back through this. Now, at low frequencies, whatever you inject here will be cancelled by whatever is coming out of there. Okay. At high frequencies, of course, this path cannot cancel it, right? So there is always a bandwidth limitation for cancellation. I mean, there are sort of two views of negative feedback you can take. The two are useful in different situations. One is the following this thing. That is, you have a target, and then you look at the actual output, and you you measure the error between the actual output and the desired output, and you go on adjusting the output. This is like following some target. Okay. The other is cancellation. I mean, this is also like following, but in the opposite way. So you send something. I mean, this is the kind of thing that you would use in, let's say, noise cancelling headphones and so on, right? There is some noise coming in, and then you have to sense and measure how much it is, and then cancel that. So that feedback loop takes some time. So this cancellation will always be effective only up to a certain frequency and no more, because beyond that you cannot like follow that noise and then cancel that. So this is high pass. What it means is any low frequency phase noise of the VCO, right? That's okay. That will get corrected by the loop. Okay. Whereas at very high frequencies, if it is jittering around at very high frequencies, nothing can be done. It just comes straight out. Okay. This is fine. Yeah. And then the other two are essentially related to this. This, of course, is a scaled version of phi ck by phi d, and this one is injected somewhere in the middle of the loop, so it has a band pass type function. Okay. Now you also realize why I gave you that problem in the first assignment, where you have to calculate the integrals of these things, and that's useful here to calculate integrated jitter and so on. Okay. So now we have the expressions. Please plot this with the assumption. Please plot these things. You can assume that omega z is substantially smaller than omega u, and then you can find an approximation for the poles, and then you plot it. Okay. This is fine. So now we have clock and data recovery circuit without a forwarded clock. So that is good. So this is what is widely used also in, especially when you have longer links. Now whether you use forwarded clock or not, it depends on many trade-offs. Typically when you have lots of lanes, right, lots of parallel lanes, and a relatively short distance between the transmitter and receiver, you tend to use a forwarded clock, because already you have so many data lanes, like one more lane for the clock is not such a big overhead, and it simplifies the design like substantially, right? So the transmitted clock is there, you don't have to recover the frequency and so on. So that's why you use it. But when you have a single line, and especially one which spans a longer distance, then this is a significant overhead to use another link just for the clock, because if you do have another link, you may put it to use for data, right? That's a lot more productive. So then you try to recover the clock from the data. Okay. So please plot these things, and we'll continue the discussion.